Hey everyone, my name is Nicholas Harper, and this is my Module 11 assignment for Manufacturing System Simulations for MFG 515. These are just the questions we had for this week assignment. I decided to just go ahead and make a little PowerPoint with some notes and just do a voiceover. I thought that would be the easiest. So what is terminating simulations and what is the steady state simulations? Once you have defined these, please give an example of each, preferably not from the supplied articles. So in terms of just terminating simulations, it's just simulations that will begin at a defined state or time and will end when it reaches another defined state or time. So basically, it's just an overall system that will start empty and then it will end in that same empty state once it's run its course for that day or week or how long, and it will never be in that steady state like the steady state simulation will be. So just an example I was thinking of, because I didn't want to use some of the stuff we used, I just went with a bank. Banks are pretty much a perfect example of terminating simulations. They open at the same time every day. There's always no customers when they open. They can work their 8 hours and close at a certain time with no more customers present, or they can work their whole week and do it like that. But they will always start empty and end empty. And then there's the steady state simulation, and this one's just no defined starting and stopping points. After the warm up period, it will eventually become a stable process in time. So it's just going to be another system, but this one's going to be more of just continuous process that will have to happen over and over, and will eventually reach that steady state once that warm-up period is over. And for this example, I actually work at New Flyer, and we make buses. So I just decided to throw that one in because we have several shifts. It's always moving. Something's always happening. We're never starting empty and ending empty. So we're definitely a good candidate for this non-terminating or steady state simulations because we're never shutting down. It's always continuing. Yeah. So why are many of the formulas from classic statistics as taught in statistics class not directly applicable to the analysis of simulations output data? And please illustrate your answer with an example. So the formulas to work from these classical, statistic, math class, the variables that we used in that math class uh, are being used, and they're different from the ones we're using in the simulation data because they have to be independent, identical, distributed, or as it's called, IID. So in other words, these IIDs are, like I said, independent, identical, or distributed, but they're just in terms of they're just random samples and probability, uh, and these random samples they occur throughout the simulation. Um, they're not connected to each other, but independent in some way. And when it comes to doing these more classical statistical math problems and these variables, they're not going to be IIDs. Most of them formulas that we would do, uh, they're not mutually independent, which means they can't be IIDs. So the example I decided to go with was just something easy, just tossing a quarter in there. Everybody's done it. You toss a quarter in the air 10 times, you have no idea what it's going to land on. It could be heads or it could be tails. And when you toss it the first time and it comes down and it's heads, well, the next time you toss it, there's no way for that last toss to have any kind of effect over the next outcome. There's no way for it to pursue that next flip to be heads or tails. So each toss is independent and will always have a 50% chance of either being heads or tails. Okay, why may a warm-up period be necessary to produce suitable simulation output data? What is an optimal warm-up period? What is recommended minimal number of cycles for warm-up? So why do we need warm-ups? We need these warm-ups for when we use the steady state data in simulations. We're going to need that warm-up period for when we break down the data at the very end, and we don't want that warm-up period to be mixed in with the final analysis of the entire steady state simulations. So once that transistor mean curve flattens out, we can then determine the initial transient or the behavior in those beginning stages when we were trying to get this data in the simulation, and then we can end up deleting that data so it doesn't interfere with the data we need. So then that warm-up data doesn't mix in with the steady state data. So a good warm-up period won't be too small or too big. Both factors could affect the final data at the end of the simulation. To determine the supposed to be appropriate warm-up period, you must determine when the transient mean curve flattens out in the simulation, like I just said. So how are we going to do this? Well, there's methods coming up in the next question, but I decided to go ahead and put Welch's method in here because just one of the methods that we get to read about that just kind of briefly explains to us how we can determine this. And just using that graphical method he has in the articles is just one way to determine the warm-up period and how many cycles are needed to determine this data. You can physically look at the data, the graph of the data, and compare that Q to the overall time it's taken to kind of reason out the initial transient data. I believe Curry and Ching defines that simulation to be ran at least 5 times or is greater than equal to 5 for this method to work. So over 5 times, I believe, is just the minimal amount that needs to be run. So describe the 3 popular types of methods for determining optimal warm-up time for the simulation model Bs, and then which one of these would you choose to choose when running a simulation and why? So obviously there was 3 main ones that were in the articles, and like I just said in the last question, there's Welch's method, and that one's more focused around that graphical approach like I was talking about, and examining the more times series outputs, in my opinion. It's obviously this one's one of the more simpler ones and easy versions when it comes down to trying to understand and determine that warm-up time. Like I said, they suggest running it at least 5 times just to get the model going. And then once you have that model, then you can calculate that overall mean of the data. And then going from there, I believe you go for the average. Once you get that average, you can then start plotting those averages and versus the Q versus time. And then if the data doesn't look like it should, just keep running the simulation more and more. I mean, that can never hurt. And then once you can see it, that warm-up period on the graph, then you can start figuring out that warm-up time. So the next one is MESR-5. These were definitely different approaches. Just read them. It uses simple rules, but a lot more equations to determine this warm-up length. This process also involves using these batches now and plotting the averages of the numbers. These were a little confusing. It is just an algorithm, like I said, based on batch. It is trying to figure out just that minimum data. And then the next one was batch means. And this one, it's just another method. To me, it was more complex than the last one for trying to determine that warm-up process, in my opinion. It focuses on splitting up the data, I believe, in the output, and then using those batches again for trying to mash it up with length in some way, and then trying to determine what b equals uh, in the equation. So why is it unacceptable to perform just a single run for a model and then use its output data in decision making? I think this one's probably one of the easier questions because I mean it depends on the model, of course, but every simulation should be ran multiple times to gather that better average of data and then compare it to the running one time. It's just one simulation compared to running it out 50 times. You just get such a better answer that you want. And of course, several replications should also be done in simulation models because anything can happen in simulation. We looked at previous models where simulation can throw in crazy events that are very rare but could happen, and that could always just throw off your data for some reason because no model is going to be perfect, so it needs to be ran several times, if not tens of times, like just several times, just so you get them the accurate answer that you're either paying for or getting somebody to figure out for you. So, what is the significance of confidence intervals and how are they determined and why are they necessary? So, confidence intervals they're just a range of values for the parameter itself that are based off the simulation results and the data it provides us at the end. Um, these intervals can provide us with data and information of relationships when it comes to actual data for the simulation, and then it can give us expected values, specifications we're trying to achieve based off the numbers of runs the simulation actually goes through. So why do we even need them in the simulation and the reasons we go through to get them? It's just the most important reason I think is that these intervals are basically will show us the operator or user if the simulation has been run enough. I know the articles talked about these intervals that can you can see if the number is way too large, then we need to run the simulation more, but if the numbers are too small, then we need to run it less to get it in that perfect little spot. And then, of course, these intervals can also help us validate the model in the long run, which, like we talked in the past, is super important when it comes to these simulations, and just bases that off that curve of these intervals could help us uh, just with like that overall validation and making sure the data is lined up with the actual data in the end compared to the estimated. So what is an MM1Q, and give an example from everyday life that illustrates this concept. So an MM1Q is it's a queuing theory that will represent the queue's length in a system with just a single server, or it's one activity that's being performed in a system from an individual that they must complete. It uses the Poisson process, which is just arriving, or it's arriving, which means it does model uh, these random events that occur in the system. And I saw some of the, or just read some of the, like what are the qualities that this MM1Q has to possess. The more I thought about the qualities and tried to make an example with it, and I thought it was a pretty good example is just cars on a highway. It's super general. It hits all the same qualities that these MM1Qs and Poisson processes are trying to do. And it's just the number of cars we see on the highway at one system, there's always going to be a lot. There can be all types of cars, slower, faster, newer, older, and a single car itself uses just a small percentage of the highway. So it's one car out of hundreds or thousands. And then, of course, the decision to even get on the highway, it's its own decision made by the car who's driving. So I think this matches up very good with the poison arrival process and just kind of similarities they both share, because there are conditions that need to be met. So I think that does match up very good when it comes to just a simple and easy understanding example. So why is a warm-up period unnecessary for a terminating simulation? And what are some key considerations for starting a terminating simulation correctly? So like we said in the beginning, terminating simulations doesn't require that warm-up period. They start and stop only during simulations. And just some basic key assumptions I think that should be noted would be we got to know how long we are measuring these time frames for in these simulations. I think that plays a big part in these simulations. And if it's just a store, how do we want to do the simulations? Do we want to do it for 8 hours, just like an 8-hour workday, 6 in the morning, 4 in the afternoon, or do we want to do it for a week? Do we want to do that whole 40 hours and compare? I think that all plays a key part in why we would need to consider that. I think another key consideration would be the operator. How well do they know the system? They're trying to run through a simulation on some of the machines. What kind of, is this like a machine shop? Is it a hospital? How heavy does this business or company rely on these heavy machineries to produce its products? What if the machines go down? I mean, anything could happen, and some of this stuff should be considered key considerations. But back to the main point, why is a warm-up period unnecessary? Well, when a warm-up period is for that time period where it takes to warm up itself to be ready to go. That could take 5 hours, that could take 30 minutes. Here at New Flyer, when we start up, of course, people have to go get their tools, get their prints. I mean, it takes us a minute to get going, but I mean, once we get going, it's a pretty stable rate, and I mean, we're going. So when you are just a terminating simulation, then you get there and you start, you don't have to worry about that warm-up period at all. So ultimately, a simulation model will be used to help a practitioner make an informed decision regarding system changes. How can simulation data lend itself to making these decisions? Please give an example of how a practitioner could use simulation data to decide regarding one system configurations over another. I thought this was a great question considering the assignment we had last week. We were given just a simple question with factors and considerations about an operator with an old machine and a new machine. I think that fits perfectly into this question. You have an old machine, it takes longer to process. You have a newer machine, it takes shorter to process. The big factor is that operator has to be at that old machine for 10 minutes that entire time. He can't leave until that process is done. You have this newer machine, it takes 6 minutes to process, but he don't have to be there. Once it starts, he's good. So I think looking at that simulation, you see how much little that new machine can process only because the operator is not there half the time. I mean, he's at the old machine the majority of those, I think it was 16 hours. He's at that old machine almost the entire time. But if he had these two new machines in place of the old machine, then he could go back and forth and they would process 10 times better because he wouldn't have to just stand there for 10 minutes at a time. So I think these simulations can definitely help an operator or practitioner make that kind of decisions, because you can literally see the data, you can see the charts, you can see how good these machines were processing, which one did better, which one did worse. how much they process, and I think that really has an effect on how well these simulations could play out in just the data alone.